Tonight, we are going to take a slow and quiet journey into the world of atoms. Not as a difficult science lesson, not as something you need to memorize, and not as a collection of diagrams, formulas, and test questions, but as a soft exploration of the tiny pieces that quietly build the world around you. Atoms are far too small to see with your eyes, and yet, everything you can touch is made from them. The air in the room, the water in a glass, the fabric of a blanket, the wood of a table, the minerals in stone, the calcium in your bones, the carbon in your skin, the oxygen moving gently in and out of your lungs. All of it is made of atoms. Tiny, quiet, invisible pieces of matter. You do not need to understand everything tonight. You do not need to remember every term. If your mind begins to drift, that is perfectly okay. This video is not here to keep you awake. It is here to let science become soft in the background. A slow story about matter. A quiet walk through the small hidden structures of the world. So let your breathing settle. Let your body become a little heavier. Let the day begin to loosen its hold. And imagine, for a moment, that we are gently zooming in. Closer and closer. Past the surface of a table. Past the smoothness of glass. Past the softness of cloth. Past the tiny grains of dust floating in the air. Closer than the eye can see. Closer than a microscope can comfortably show. Down into the quiet world of atoms. Welcome to Gentle Chemistry. Tonight, we are exploring atoms, slowly and calmly, before bed. Before we begin with atoms themselves, let's start with something familiar. Matter. Matter is anything that has mass and takes up space. A stone is matter. A drop of rain is matter. A cloud is matter, even though it looks soft and weightless from far away. The air around you is matter too. It may feel invisible. It may feel almost like nothing. But air is made of tiny particles. Nitrogen, oxygen, argon, carbon dioxide, water vapor. And those particles are made of atoms. Some matter is solid. It holds its shape. Like wood, metal, ice, glass, or stone. Some matter is liquid. It flows and takes the shape of its container. Like water, oil, honey, or rain. Some matter is gas. It spreads out and fills the space around it. Like air, steam, helium, or the scent of flowers drifting through a room. But whether matter is solid, liquid, or gas, it is still built from tiny particles. And at the heart of ordinary matter, there are atoms. Atoms are like the small letters from which the physical world writes its words. One atom by itself can be very simple. But atoms can combine. They can arrange. They can bond. They can form molecules, crystals, metals, gases, liquids, and living cells. That is one of the quiet miracles of chemistry. The world is large, colorful, and complex. But underneath it, there are tiny patterns, tiny structures, tiny pieces, patiently becoming everything. The word atom comes from an old idea. Long ago, some ancient philosophers wondered what would happen if you took a piece of matter and kept cutting it into smaller and smaller pieces. Imagine a piece of gold. You cut it in half, then in half again, then again, and again. At some point, they wondered, would you reach a smallest possible piece? A piece that could not be cut any further while still remaining the same kind of matter? The word atom comes from a Greek word meaning something like uncuttable. The ancient idea was not exactly the same as modern atomic science. But the question was beautiful. How small can matter become? What is the world made of when we go all the way down? For a very long time, atoms were not something people could directly see or measure. They were an idea, a possibility, a way to explain change, mixture, and the different kinds of matter. But as science developed, the atomic idea became stronger. Chemists noticed that substances reacted in consistent proportions. Gases behaved in patterns. Elements combined in predictable ways. And slowly, atoms became more than a philosophical thought. They became a scientific explanation, a way to understand why matter behaves the way it does. Today, we know atoms are real physical structures, not little solid balls exactly, not tiny planets with perfect circular orbits, but structured systems made from smaller particles. A nucleus in the center, electrons around it, mostly empty space. And yet, from that almost empty structure, the solid world emerges. This is one of the strangest and most peaceful thoughts in science. The world feels solid. A table feels firm. A stone feels heavy. A wall feels still. A glass of water feels like a continuous smooth liquid. Your hand feels like one complete thing. But deep inside, matter is mostly space, shaped by forces, energy, and tiny particles. This can be one of the most surprising ideas in all of science. Forces push and balance. Structures hold. Bonds connect. But the atom itself is not packed full like a tiny marble. It is more like a small center surrounded by a wide, soft region of possibility. If the nucleus were enlarged to the size of a tiny bead, the rest of the atom would stretch far outward around it. Most of that space would not contain solid material in the everyday sense. And yet, from this spacious structure, we get wood, stone, glass, water, metal, and skin. The solid world is made from things that are mostly not solid. This is not meant to feel unsettling. It can feel peaceful. The firmness of the world is a kind of agreement between particles and forces, a stable pattern, a quiet balance. When you rest your hand on a table, the atoms in your hand and the atoms in the table do not pass through each other, because the invisible forces between them resist that motion. You feel solidity because of interactions, because of electrons, because of structure, because matter is not just stuff, but relationship. The spaces inside atoms are not empty in a lonely way. They are part of the atom's architecture. Soft, invisible rooms where energy, charge, and probability create the physical world. So when you look at a quiet object nearby, you can imagine it differently. Not as something dull and solid all the way through, but as a vast arrangement of tiny centers and soft electron clouds. A hidden field of structure. A still object made of almost unimaginable space. And that space is held together gently enough to become the world you know. Let's picture an atom very gently. At the center is the nucleus. The nucleus is extremely small compared with the whole atom, but it contains almost all of the atom's mass. Inside the nucleus are protons and neutrons. Protons have positive electric charge. Neutrons have no electric charge. Together, protons and neutrons make the dense center of the atom. Around the nucleus are electrons. Electrons have negative electric charge. They are much lighter than protons or neutrons. They do not sit in simple, neat little circles like planets around the sun. That picture can be useful at first, but the real electron world is softer, stranger, and more cloud-like. Electrons exist in regions of probability, places where they are likely to be found. These regions are called orbitals. You do not need to picture them perfectly. You can simply imagine a soft cloud around the nucleus. A cloud of possibility. Not a hard shell. Not a tiny solar system. But a quiet, delicate structure where electrons belong to the atom. The atom is held together by electric attraction. The positive protons in the nucleus attract the negative electrons around it. Opposite charges pull toward each other. This attraction helps keep the atom together. And yet, the electrons do not simply fall into the nucleus. The quantum world has its own rules. Electrons exist in allowed energy states. They can gain or lose energy. They can move between states. They can help atoms bond with one another. So even though atoms are tiny, they are not simple in a boring way. They are simple and mysterious at the same time. A small center. A surrounding cloud. A balance of charge. A a structure that can build everything. Now let's pause with the nucleus. The nucleus is the atom's dense heart. It is where the protons and neutrons are found. If an atom were enlarged to the size of a large stadium, the nucleus would be like something tiny near the center, and the electrons would occupy the surrounding space. This means the atom is mostly empty space. But that empty space is not nothing. It is filled with fields, forces, and probability. It is structured emptiness, a soft, invisible architecture. The protons inside the nucleus are especially important because they determine what element the atom is. 1 proton means hydrogen. 2 protons means helium. 6 protons means carbon. 8 protons means oxygen. 26 protons means iron. 79 protons means gold. This number is called the atomic number, and it is one of the most important ideas in chemistry. The identity of an element is not determined by its color, or its shape, or where we find it. It is determined by the number of protons in its nucleus. If an atom has 6 protons, it is carbon. If it has 8 protons, it is oxygen. If it has 79 protons, it is gold. If you change the number of protons, you change the element itself. This is why the periodic table is arranged by atomic number. It is a list of elements ordered by the number of protons in their atoms. 1, 2, 3, 4, and onward. A slow staircase of matter. Neutrons are quieter. They do not have electric charge, but they are still important. Neutrons help stabilize the nucleus. Atoms of the same element can have different numbers of neutrons. These are called isotopes. An isotope is still the same element because it has the same number of protons, but it has a different number of neutrons. For example, carbon always has 6 protons. That is what makes it carbon. But carbon atoms can have different numbers of neutrons. Carbon-12 has 6 neutrons. Carbon-13 has 7 neutrons. Carbon-14 has 8 neutrons. They are all carbon, but they are different isotopes. You do not need to remember those numbers tonight. Just notice the gentle idea. Protons give the element its identity. Neutrons can change the atom's weight and stability. Some isotopes are stable. Some are radioactive, which means their nuclei can change over time. This may sound complex, but the basic picture is simple. Atoms have a center. That center has protons and neutrons. The number of protons names the element. The number of neutrons can create different versions of that element, like different editions of the same quiet book. The title is the same, but a few pages inside are different. Now let's come back to the electrons. Electrons are light, negative, and deeply important for chemistry. Most chemical reactions happen because of electrons. Atoms bond because of electrons. Atoms gain, lose, or share electrons. Molecules form because electrons allow atoms to connect. So if the nucleus gives an atom its identity, electrons help determine its behavior. You can imagine the nucleus as the name of the atom, and the electrons as the atom's way of reaching out into the world. Electrons live in energy levels. The lowest energy levels are closest to the nucleus. Higher energy levels are farther away. The electrons in the outermost level are especially important. These are often called valence electrons. Valence electrons are the ones most involved in bonding. They are like the outer hands of the atom, the parts that can reach toward other atoms. Some atoms have outer electron arrangements that make them very stable. These atoms do not easily bond. The noble gases are like this: helium, neon, argon. They are chemically calm because their outer electron shells are full. Other atoms are less settled. They may need to gain, lose, or share electrons to become more stable. This is one of the reasons atoms form bonds. They are not lonely in a human sense, but they can become more stable by connecting. And from those connections, chemistry begins. There are different kinds of chemical bonds. We can touch them only lightly tonight. just enough to see how atoms come together. One kind is an ionic bond. This happens when one atom gives an electron to another atom. The atom that loses an electron becomes positively charged. The atom that gains an electron becomes negatively charged. Opposite charges attract, and the atoms hold together. Table salt is a familiar example. Sodium gives up an electron. Chlorine gains an electron. Sodium becomes Na+. Chloride becomes Cl-. Together, they form sodium chloride. Salt. Tiny crystals. Something ordinary on a table. But inside, it is a calm pattern of charged particles held together by attraction. Another kind of bond is a covalent bond. This happens when atoms share electrons. Water has covalent bonds. Each water molecule contains 2 hydrogen atoms and 1 oxygen atom. The oxygen shares electrons with the hydrogens. Together, they form H2O, a tiny bent molecule. So familiar in the world. Then, rivers, clouds, tears, snow, steam, all from atoms sharing electrons in small arrangements. A third kind of bonding appears in metals. Metal atoms can share their outer electrons in a more collective way. Those electrons can move through the metal. This helps explain why metals conduct electricity and heat. Copper wires work because electrons can move. Iron tools, gold jewelry, aluminum foil, silver mirrors, all have their own metallic structures. Again, atoms and electrons are quietly shaping the properties we see. If some of that felt like a lot, you can let it soften. You do not need to sort every bond into a category tonight. Just keep the simple image. Atoms have electrons. Electrons allow atoms to connect. Some atoms give electrons. Some atoms receive electrons. Some atoms share electrons. And when atoms connect, matter changes. A gas and a metal can become a crystal. 2 gases can become water. Carbon atoms can arrange into graphite or diamond. Tiny differences in atomic arrangement can create enormous differences in the world. This is why chemistry is not only about what something is made of. It is also about how it is arranged. The same element can become different materials. The same atoms can create different shapes. The same letters can become different words. And in the quiet language of matter, arrangement matters deeply. Let's explore a few atoms slowly. We can begin with hydrogen. Hydrogen is the simplest atom. 1 proton. 1 electron. Usually no neutron in its most common form. It is the first element on the periodic table. The lightest element. The most abundant element in the universe. Hydrogen is simple, but not unimportant. It fills stars. It helps stars shine. It is part of water. It appears in many molecules of life. When you see the formula H2O, those 2 H atoms are hydrogen. When you think of the sun shining, hydrogen is part of that story too. In stars, hydrogen nuclei fuse together under immense heat and pressure. That fusion releases energy. And that energy becomes starlight. So the smallest atom is connected to some of the largest and brightest things in the universe. A single proton. A single electron. And yet, hydrogen belongs to water, life, and stars. Helium is next. 2 protons. Usually 2 neutrons. 2 electrons. Helium is light and calm. It is a noble gas. That means its outer electron shell is full. It does not easily react. It does not need much from other atoms. It is chemically peaceful. You may know helium from balloons that float upward. But helium also belongs to the stars. Inside stars, helium can form from hydrogen fusion. Helium is simple, stable, and quiet. It reminds us that not all atoms are eager to bond. Some atoms are already complete in their own way. Some atoms drift. Some atoms float. Some atoms simply exist, calm and self-contained. Carbon is different. Carbon has 6 protons. Carbon is one of the great builders of chemistry. It can form 4 strong covalent bonds. It can bond with itself. It can make chains, rings, branches, sheets, networks. This makes carbon incredibly important for life. The molecules in your body are built around carbon frameworks. Sugars, proteins, fats, DNA. Carbon is like a quiet architect. It can build small, simple molecules, and it can help build enormous, complex ones. Carbon also shows how arrangement changes everything. Graphite and diamond are both made of carbon. In graphite, carbon atoms form sheets that slide over one another. That is why graphite is soft enough to leave a mark on paper. In diamond, carbon atoms form a strong 3-dimensional network. That is why diamond is so hard. Same element, different arrangement, different material. One dark and soft, one clear and hard. Chemistry is full of these transformations. Oxygen has 8 protons. Oxygen is familiar because it is part of every breath. The oxygen gas in the air exists as molecules made from 2 oxygen atoms. O2. When you breathe in, oxygen enters your lungs. It passes into your blood. It travels through the body. It helps your cells release energy from food. Oxygen is also part of water, part of rocks, part of the atmosphere, part of fire. When something burns, oxygen is involved in the reaction. It helps atoms rearrange in a way that releases heat and light. So oxygen belongs to both breath and flame, to life and burning, to water and stone. It is an element of movement and transformation. And all of that begins with atoms. Tiny oxygen atoms, each with 8 protons at the center. Iron has 26 protons. Iron is strong and familiar. It is in tools, buildings, machines, bridges, and old gates. It is also in your blood. Inside hemoglobin, iron helps carry oxygen through the body. Iron is also connected to stars. In massive stars, iron can form near the end of the star's life. It is a heavy and important element. On Earth, iron can rust when it reacts with oxygen and water. Rust is slow chemistry, a metal surface changing over time, color shifting, structure weakening, matter quietly reacting with the air. Iron reminds us that atoms do not only build things, they also transform them. A bridge can rust. A tool can age. Blood can carry oxygen. A star can make heavy elements, all connected by the same atomic rules. Gold has 79 protons. Gold is heavy, warm in color, and resistant to corrosion. It does not easily tarnish. It keeps its shine. This is one reason humans have valued it for thousands of years. Gold appears in jewelry, coins, art, electronics, and ancient treasures. But gold is also a story of atoms. Each gold atom has 79 protons in its nucleus. That number makes it gold. Not its shine alone. Not its value. Not its place in history. But its atomic identity. Gold also connects us to cosmic events. Heavy elements like gold may form in extremely energetic events, such as the merging of neutron stars. So gold is not only beautiful because it glows in human hands. It is beautiful because its atoms may carry the memory of ancient cosmic violence. A quiet piece of the universe, condensed into a metal that does not easily fade. Now, let's bring atoms closer to everyday life. Closer to the room. Closer to the body. Closer to the quiet, ordinary things that surround you. Atoms are not just inside laboratories. They are in your room right now. The air around you is mostly nitrogen and oxygen. Each breath moves molecules in and out of your body. If there is a glass of water nearby, it is made of water molecules. Each one contains hydrogen and oxygen atoms. If there is a window, the glass contains silicon and oxygen arranged in a solid network. If there is a blanket, it may be made from long molecules built mostly from carbon, hydrogen, oxygen, and sometimes nitrogen. If there is a phone nearby, it contains many elements. Silicon in chips, lithium in batteries, copper in wires, gold in tiny connectors, aluminum, nickel, tin, and others in small hidden parts. If there is a book, the paper is built from cellulose, a molecule made by plants. If there is a candle, its wax is made from molecules rich in carbon and hydrogen. When it burns, those atoms rearrange with oxygen, forming carbon dioxide and water, releasing heat and light. Even dust is atomic. Tiny fibers, mineral fragments, skin cells, pollen, small pieces of matter drifting gently through the air. Now let's bring atoms even closer. Into the body. Your body is not made from a special kind of matter separate from the rest of the universe. It is made from atoms too. Oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, sulfur, sodium, potassium, iron, magnesium, zinc, and many others in small amounts. Oxygen is the most abundant element in the human body by mass, largely because the body contains so much water. Hydrogen is also everywhere, paired with oxygen in water and present in organic molecules. Carbon forms the backbone of many molecules of life. It is in sugars, fats, proteins, and DNA. Nitrogen helps build amino acids and nucleic acids. Calcium gives strength to bones and teeth. Phosphorus is part of DNA and part of the molecules that help cells carry energy. Iron helps blood carry oxygen. Sodium and potassium help nerves send signals. Magnesium helps with many cellular processes. Zinc appears in enzymes and tiny biological mechanisms. You do not need to remember this list. It can simply drift by. The gentle idea is that your body is a living chemistry of atoms, a warm arrangement of elements, not fixed like a stone, not still like a crystal, but moving, breathing, repairing, sensing, and changing. Every breath brings atoms in. Every breath carries atoms out. Every sip of water becomes part of you for a while. Every meal brings carbon, hydrogen, oxygen, nitrogen, minerals, and energy into the body. Atoms become blood. Atoms become muscle. Atoms become thought, movement, warmth, and rest. And then, slowly, atoms leave again. Through breath. Through water. Through the natural cycles of the body. There is something very soft about this. You are not a fixed object. You are a changing pattern. A temporary arrangement of ancient atoms. A living chemistry that holds together for a while, gently exchanging matter with the world. The atoms in your body have been other things before. They may have been part of air, ocean, leaves, soil, fruit, stone, or rain. And long before that, many of them were part of stars. The body is not separate from chemistry. It is chemistry, awake. Chemistry breathing. Chemistry resting. Chemistry becoming aware of itself, quietly, for a little while. Atoms are also everywhere in nature. In rain, atoms gather into water molecules that fall from clouds. In clouds, tiny droplets and ice crystals float in the air. In the ocean, water molecules surround dissolved ions like sodium, chloride, magnesium, calcium, and potassium. The taste of seawater comes from atoms separated and carried as charged particles. In leaves, carbon, hydrogen, oxygen, nitrogen, magnesium, and other elements are arranged into living green structures. Chlorophyll, the molecule that helps plants capture light, contains magnesium at its center. That little fact is easy to let pass, but it is beautiful. A metal atom sitting inside a green molecule, helping leaves gather sunlight. In rocks, atoms form minerals. Silicon and oxygen build much of the rocky crust of Earth. Iron can give stones red and orange colors. Copper can create blue and green minerals. Carbon can become limestone, graphite, diamond, or the soft chemistry of living things. In fire, atoms rearrange quickly. Carbon-rich molecules react with oxygen. Bonds break. New bonds form. Heat and light are released. In crystals, atoms or ions arrange themselves into repeating patterns. Salt crystals, quartz crystals, snowflakes. Each one is a visible echo of tiny order. Nature is full of atoms becoming patterns. Rain becoming rivers. Minerals becoming mountains. Carbon becoming leaves. Oxygen becoming breath. Water becoming clouds. Ice becoming snow. Fire becoming warmth and ash. And underneath every quiet natural scene, atoms are present. Not loudly. Not dramatically. Just faithfully. Holding the world together, one small structure at a time. The world around you may seem still, but at the atomic level, it is full of structure and motion. Molecules vibrate. Particles move. Atoms hold together. Bonds stretch and bend. Heat is motion. Solids are not truly motionless. They are quiet arrangements with tiny vibrations inside. This is a good place to rest for a moment. If all these details are beginning to blur, that is completely okay. The atom can become simple again. A small center. A soft cloud. A quiet structure. You do not need to hold the whole invisible world in your mind. You can let it become an image. A tiny point of light. A gentle haze around it. A little system of matter, charge, and space. If you are becoming sleepy, you do not need to follow every detail. You can just imagine the room around you made of small, soft points of matter. The air as invisible molecules. The glass as a frozen network. The blanket as long, gentle fibers. The water as tiny bent molecules. Your body as a living arrangement of atoms. Not chaotic. Not random. But patterned. Held together by forces. Moving quietly. Changing slowly. The atomic world is not loud. It is constant. Hidden. Patient. Now let's think about size. Atoms are incredibly small. A single atom is so tiny that ordinary numbers begin to feel strange. You cannot see one atom with your eyes. You cannot feel one atom as a separate object. A single drop of water contains more water molecules than we can easily imagine. And each molecule contains atoms. This means that the ordinary world is built from enormous numbers of tiny things. A drop of water looks simple, clear, smooth, quiet. But inside it are countless molecules moving, rotating, bumping, attracting, and separating. Water appears continuous to us because the particles are so small and so many. A solid table appears smooth because its atoms are arranged far below the scale of sight. A metal spoon feels continuous and cold because atoms and electrons create the properties we experience. Our senses show us the large-scale world. Chemistry helps us imagine the smaller world underneath. And both worlds are real. The smooth surface. And the tiny structure. The still object. And the vibrating atoms. The quiet room. And the unseen motion inside it. Temperature is also an atomic story. When something is hot, its particles are moving more. When something is cold, its particles are moving less. In a solid, atoms may vibrate in place. In a liquid, molecules can slide past one another. In a gas, particles move freely and spread out. This is why ice, water, and steam feel so different even though they are all made of water molecules. In ice, water molecules are arranged into a solid structure. In liquid water, they move around each other. In steam, they separate and fly through space as a gas. Same molecule. Different motion. Different arrangement. Different state of matter. This can be a very gentle idea to carry into sleep. The world changes when particles move differently. Ice melts. Water evaporates. Steam condenses. Clouds form. Rain falls. Snow settles. The same atoms and molecules can pass through many forms. Matter is not fixed forever. It changes with energy, temperature, pressure, and time. Atoms also help explain color. Color happens when matter interacts with light. Some substances absorb certain wavelengths of light and reflect others. Some atoms and molecules can absorb energy and later release it as light. This is why neon signs glow. Electric energy excites atoms in the gas. The atoms release energy as light. Different gases can glow with different colors. Fireworks also depend on atoms and ions releasing characteristic colors when heated. Copper compounds can create blue-green colors. Strontium compounds can create red. Sodium can create yellow. You do not need to remember which element makes which color. Just notice the quiet idea. Color is not only on the surface of things. Color often comes from the way atoms and electrons respond to light and energy. A blue flame, a green mineral, a red sunset, a glowing sign in a city street, a purple crystal. All of them are connected, in some way, to atoms and light. Atoms also help explain smell. When you smell something, tiny molecules are drifting through the air and reaching receptors in your nose. The smell of rain, the scent of coffee, the sharpness of vinegar, the sweetness of vanilla, the freshness of mint. All of these come from molecules. And molecules are made of atoms. A smell is not just a feeling. It is matter, traveling invisibly. Tiny particles moving through space, meeting your senses. This is one of the most intimate forms of chemistry. A flower releases molecules into the air. Coffee releases aromatic compounds as it warms. Rain can lift earthy molecules from dry soil. Your body detects them. And suddenly, chemistry becomes memory. A smell can remind you of a place, a season, a person, a morning, a storm. Atoms become molecules. Molecules become scent. Scent becomes memory. Atoms also help explain taste. When you taste salt, sodium and chloride ions interact with receptors on your tongue. When you taste sourness, acids are involved. When you taste sweetness, certain molecules fit into sweet receptors. Bitterness, umami, and other sensations also have molecular explanations. Taste is chemistry meeting the body. A tiny interaction between matter and living tissue. When sugar dissolves on your tongue, molecules move into solution. When tea tastes bitter, plant compounds are touching receptors. When chocolate tastes rich, hundreds of molecules contribute to aroma, texture, and flavor. The experience feels simple, pleasant, immediate. But underneath, atoms are arranged into molecules, and molecules are communicating with the body. The world becomes taste through chemistry. Now let's return to something very simple. An atom is small. An atom has a nucleus. The nucleus contains protons and neutrons. Electrons exist around the nucleus. Protons give the element its identity. Electrons help atoms bond and react. Atoms can join together to form molecules. Molecules can form substances. Substances can become water, salt, sugar, glass, stone, air, wood, skin, blood, stars, and oceans. This is the quiet chain. Atoms, molecules, materials, objects, life, world. The tiny becomes the enormous. The invisible becomes the familiar. The hidden becomes everything. There is also something peaceful about knowing that atoms are shared. The atoms in your body have not always been yours. They have been part of air, water, plants, soil, animals, oceans, and ancient rocks. The carbon in your body may once have been part of a leaf, or a breath, or a tiny sea creature. The oxygen you breathe has moved through the atmosphere, through plants, through water, through living things. The hydrogen in your body may be incredibly ancient, formed near the beginning of the universe. The calcium in your bones may once have been part of old seashells or minerals. Matter moves through cycles. Atoms are borrowed, held for a while, then released. A breath enters, a breath leaves. Food becomes body, body becomes motion. Water becomes blood, sweat, vapor, rain. Atoms do not stay fixed in one story forever. They pass through many forms. And this gives chemistry a kind of quiet tenderness. You are not separate from matter. You are one of matter's temporary arrangements. A living, breathing pattern of atoms. Held together for a while. Changing slowly. Connected to everything. The atoms around you also come from the universe. Hydrogen formed very early. Helium formed early as well. Heavier elements were made later inside stars and powerful cosmic events. Carbon and oxygen formed in stars. Iron formed in massive stars. Gold and other heavy elements may have formed in violent cosmic collisions. So the atomic story is also a cosmic story. The atoms in a quiet bedroom are not ordinary in the deep sense. They are ancient. They have histories. They have traveled through time, space, stars, planets, oceans, and living things. Every atom is small, but its story can be enormous. A single carbon atom in your body may have crossed through the atmosphere many times. It may have been part of a plant, then soil, then air, then food, then you. A single oxygen atom may have been part of water, rock, air, and breath. A single iron atom in your blood may be older than Earth. When you look at matter this way, the world becomes quietly connected. Not metaphorically only. Physically. Chemically. Atom by atom. And now, as we move toward the end of this gentle journey, you can let the details soften. You do not need to remember the parts of the atom. You do not need to remember protons, neutrons, electrons, isotopes, orbitals, or bonds. You can let the words become quiet. But perhaps you can keep one simple feeling. Everything around you is made of tiny hidden structures. Atoms are small, but they are not meaningless. They hold identity. They carry charge. They bond. They move. They arrange. They transform. And from their quiet arrangements, the world appears. A glass of water. A candle flame. A piece of gold. A breath of air. A sleeping body. A star. All of them are atomic stories. Before we end tonight, there is one small thing you can do, only if it feels right. If this kind of slow, gentle chemistry helps you relax, you can subscribe to Gentle Chemistry. There will be more quiet stories about molecules, water, fire, crystals, colors, elements, and the hidden science of everyday things. You can also leave a like if you enjoyed this calm journey through atoms. It helps this little channel reach more sleepy, curious minds who might enjoy learning softly before bed. And if there is a chemistry topic you would like to hear explained slowly, you can leave it in the comments. Maybe molecules. Maybe water. Maybe fire. Maybe carbon. Maybe crystals. Maybe the chemistry of color. Or maybe the quiet chemistry of rain and clouds. But for now, there is nothing else you need to do. No more remembering. No more studying. No more holding onto the details. You can let the atom fade in your mind. Let it stop being a diagram. Let it stop being a lesson. Let it become something softer. The nucleus becoming a tiny point of light. The electrons becoming a soft cloud around it. The cloud becoming mist. The mist becoming darkness. And the darkness becoming rest. The atoms are still there. In the air. In the water. In the blanket. In your breath. In the quiet matter of the world. But you do not need to follow them anymore. You can simply rest. Let hydrogen drift like starlight. Let carbon settle like a soft framework. Let oxygen move gently with your breathing. Let iron rest deep and still. Let gold glow faintly, then fade. Let all the atoms become small quiet lights. Not asking to be named. Not asking to be understood. Only glowing softly in the background of sleep. And if the idea of atoms is still with you, let it become very simple now. A tiny center, a soft cloud, a little space, a quiet pattern. Then let even that fade. Let the atoms in the room continue without your attention. Let the air move slowly. Let the molecules in the water rest. Let the fibers of the blanket hold their shape. Let the minerals in the walls stay still. Let the carbon, oxygen, hydrogen, and nitrogen of the living world continue their long cycles. You do not need to guide them. You do not need to name them. You do not need to understand them tonight. The tiny world can take care of itself. The atoms can keep moving. The molecules can keep vibrating. The bonds can keep holding. The world can keep being quietly made of matter. And you can simply rest. Thank you for spending this calm moment with gentle chemistry. If you are still awake, I hope the world feels a little softer and a little more interesting. And if you are beginning to drift away, let the tiny world of atoms become distant and quiet. Let the molecules keep moving slowly in the dark. Let the science become a whisper. And let yourself sleep. Good night.